Alright, so last week here. Last week we looked at magmatical deposits. On Monday we looked at hydrothermal fluids that are derived from magmas, and today we'll look at ore deposits formed by hydrothermal fluids that are more distally related to magma or not at all. And for instance, this is a thermal resort in the Alps, where heaps of people enjoying hot water, hot baths, and this is somewhere in an undersea volcano where we have these like smokers that release metals into the sea. So today we will look at well, the source of fluids and water, and the movement of these waters, what drives movement of waters in the crust. We'll look a bit more at metal solubility and precipitation from solutions, and then we'll look in a bit more detail at a series of deposits. And these are treated in Chapter 3 of Introduction to Forming Processes and Chapter 3 and 4 of ore deposit geology. So as I mentioned last week, or no, Monday, yes, we looked at magmatically derived hydrothermal fluids, and today we will look at fluids derived from metamorphic waters, DAGENESIS, and other environments or environmental. So there is, as everything else in nature, no clear-cut distinctions or no black and white. Last Monday, the last deposits we looked at were epithermal gold, and there is some kind of continuum between epithermal and VHMS and SEDEX that we look at today. And these deposits are usually sources of copper, lead, zinc, and gold. So the type of fluids. On Monday we looked at magmatic fluids. Today we will look at these other in green, meteoric fluids, which is basically rain percolating into the ground. Seawater, which is the same but from the sea, percolating into the ground and becoming groundwater. CONNATE fluids, if you remember I mentioned them in the first lecture, the example of the liquefaction in Christchurch, where we have basically water within porous sediments being squeezed out. And metamorphic fluids, which derive from dehydration in response to increasing pressure and temperature when we break down certain mineral assemblages. Starting on CONNATE waters, as I mentioned, when sediments are usually deposited underwater, in lakes or in the sea. So there is a lot of water available in the interstitial spaces between the sedimentary particles. And as we start to deposit more and more stuff on top of these sediments, well, the pressure increases and we start to squeeze out water. And as you can see from this graph, where we've got depth increasing here, and the rate of water release, and two lines, one for clays and one for sands. You can see that clays basically initially release a lot more water than sands. And another feature of the clays is that as the temperature increases, we have basically the water contained in the clay minerals, in the crystal structure of clay minerals, is basically squeezed out, and so we have these spikes of water release as these reactions occur. And another thing, this is a plot of oxygen and hydrogen isotopes of waters, and this is the meteoric water line. So rain usually plots on this line. We've got metamorphic waters and primary magmatic waters here in these fields. And in these basins in North America, we see that there is a range of composition in the basin water. the isotopes of the water from the sediments ranges from nearly meteoric to nearly metamorphic or magmatic. So in these spaces there are several processes that go on. The deeper you go, the closer you get to the country of and metamorphic or magmatic fluids. The next step, as we increase the temperature, as you can see from this graph, going from 0 to 600 degrees temperature, and the proportion of water released. What we just saw were the CONNATE fluids, so we had initial squeezing out of water just from the pores within the sediments, and later on these release of water from the breaking down of clays. But as we keep increasing the temperature by burying the sediments, we start to have other mineral reactions with CONNATE, which is a clay mineral, reacting with quartz to form pyrophyllite, which contain less water in the crystal structure, and so we've got this dewatering event. Later on, muscovite and chlorite react to form biotite, again, two relatively water-rich minerals react to form a water pura mineral, and so all the water comes out. And later on also biotite and quartz react to form garnet, and that's basically the last watering event, because garnet is an anhydrous mineral. So once we have all these these fluids in sediments or metamorphic fluids or whatever, well, we need to move them, because if we just leave the fluids where they are in the crust, in a basin, no movement, well, nothing's going to happen. So in order to really form more deposits, we need fluid movement and deposition of metal somewhere. So there are several mechanisms to control the movement of waters. For instance, gravity. As we are uplifting some region, of course gravity causes water to flow downhill. And that can create large-scale fluid movement. This orogeny driven, where we have compression, so on mountain building. In addition to uplift, we also have compaction, so increasing pressure. And we have dewatering through squeezing of sediments, sedimentary rocks, as well as metamorphic reaction, which release fluid and cause this flow. Another way of causing water or fluids to move is heat. Basically in mid-ocean ridges or in intra-cratonic rifts. We have the crust thinning, and heat from underneath basically driving convection cells, which can then basically allow water to flow from certain regions to other regions. And also when we are kind of fracturing rocks, changing the dynamics, we maybe first of all changing where the water table is located, and also by fracturing and faulting we create pathways where fluid can basically migrate and find their way to the surface. However, water movement is not sufficient by itself. What we need in order to form more deposits is basically the water picking up some ligand source. If you remember, a lot of metals are more soluble in hydrothermal solution if you have some kind of complex. So we need a ligand source, we need a metal source. And once we have the two, basically we can have the fluids migrating and depositing. If we have a trap, we can form more deposits either by mixing of fluids, phase separation through boiling, where we release maybe some gases, and that causes complex instability, breakdown, and metal deposition, or maybe reaction, fluid-water reaction. And after that, the fluids can kind of migrate and go to the surface, and the people can enjoy the thermal springs in them. Another thing to point out is that in order to generate viable large ore deposits, we actually need this process to go on for quite a while with large volumes of water. And I remember when I was learning this in Perth, the lecturers used to like to use the unit of measurement Sydney Harbour, which probably doesn't mean much to someone who's never been to Sydney, but it's a whole lot of water. And you needed several Sydney harbours to flow through the system to generate basically ore deposits that were viable to mine. So what causes then metals to precipitate? For instance, a decreasing temperature. As you can see, we've got temperature decreasing, and this is a measure of the stability of metal complexes. And here we've got, for instance, uranium chloride and lead chloride and zinc chloride and whatnot. So as we decrease the temperature, the solubility of these complexes basically decreases. And so decreasing the temperature might cause complexes to break down and the metals to precipitate, and that's what happens often in epithermal gold deposits or in deposits on the ocean floor, VHMS deposits, where very hot solutions in hydrothermal fluids at 350 degrees or more basically contact seawater at the seafloor, 2 to 4 degrees, and instantaneous freezing. Another way of precipitating metal from solution is by boiling. Basically, by decreasing the pressure rather than increasing the temperature. So if we want to boil some water here, we need a heater, something, stove heater. Turn it on and we boil the water with eggs. If we want to cause this process in the crust, it's much easier rather than adding temperature from underneath. Is by letting the hydrothermal fluids flowing towards the surface. We have decreasing pressure, and so we go from liquid water to vapor on the phase diagram. And this can happen along faults or shear zones. When we have movement, we might generate these dilational jogs, which is basically generating a void within a rock. So a generation of a vacuum where the fluids can suddenly rush in. It's a low pressure that causes separation of boiling and separation of metals and gas. Like the example here with gold, the bisulfide complex, so in solution, that boils and just leaves the gold precipitating and the gas released. Third way of precipitating metals from solution is by mixing. So if we mix basically hotter fluids that are mineral rich, we can kind of cause them to also lose temperature, and hence the complexes will dissociate. Either by reducing the temperature or by reducing the pH, for instance. So in the example, we've got, again, the gold as a bisulfide complex, and by basically reducing or increasing the pH and reducing the temperature, we will cause dissociation and precipitation of gold. And this is an example from 2 volcanoes in Japan, where we basically have Kirishima volcano and Esan volcanoes. Both have active hydrothermal systems, But in this system here, we don't have too much interaction with. Oh, sorry.
Do you expect us to know these equations?
No. If you know them, it might be a bonus. But as long as you understand the principles. Yeah? Right. The small system where we got little input of meteoric waters, we've got little mixing, and therefore the fluids at these volcanoes will be more metal rich once they reach the surface or when they escape the system. And again, on the oxygen and the hydrogen isotope diagram, this volcano has closer characteristics to the magmatic water. In the large volcano, where we have a larger input of meteoric fluids, these mix more thoroughly with the hydrothermal fluids from the magmatic system. And so the precipitation of metals occurs inside the volcano, and when the fluids reach the surface, they are metal poor. So in future, if you are interested in ore deposits, you might want to go and look in more detail at this one rather than where metals basically dispersed in the atmosphere. The last way is by reaction with the host rock. And that can alter the pH of the hydrothermal fluids, especially if we react an acid solution with some kind of carbonate rock. That's kind of first year geochemistry or chemistry. The carbonate, calcite in this case, reacts with hydrogen and forms carbonic acid. What influences this is that once we remove the hydrogen from the solution, basically this reaction occurs, and so we have the precipitation of sphalerite because of the stabilization of the chloride complex. Another thing to note here is that if we have a reaction between a fluid percolating and a rock, well, we want to end up with a metal or with an ore mineral that has a lower molar volume than the original material. This is a list of molar volumes, and calcite 37 centimeter cube per mole, as opposed to sphalerite, which is 24. So the more this reaction goes on, actually the more space is generated for further fluids to flow. If the opposite were true, well, we would just clog the system with this reaction and no more flow would be possible. So at a glance, we've got basically precipitation can occur by reaction with whole rock, for instance, with the fluids percolating, reacting with the rock, and precipitation of whole minerals occurs there. By boiling, as we reach shallower pressure or shallower depth in the crust and lower pressure, we've got the vapor separation and the boiling, but then generates or precipitates all minerals. Or by mixing deeper, hotter solution, maybe more acidic, with a shallower, cooler, more neutral solution, and we have the precipitation of minerals there. So if you understand things like this, you'll be a long way doing well. What is this? What does it look like? Something you use when you sleep. What are they indicative of? Underwater? Yeah. Eruptions underwater. So now we go and look at a particular deposit type. which occurs in a submarine environment. And you probably want to pay particular attention to what I'll tell you about these VHMS deposits, because the knowledge might come handy sometime very soon. And I shall say no more. So VHMS stands for volcanic hosted massive sulfides, which is the same thing as VHMS, volcanogenic massive sulfides. And they occur, as I said, on the seafloor through solution and hydrothermal venting. And as you can see, basically here in the north of New Zealand, along the Kermadec Arc, or along the East Pacific rise and mid-ocean ridges. Especially here, this is kind of a continuation of what we have in the Taupo volcanic zone on land. So VHMS deposits are sources of mainly copper and zinc, as well as lead. They form from hot hydrothermal solutions when these vent on the seafloor, and remember, venting very hot solution and very cold water causes it to precipitate the metal. And the metals actually not coming from a magma source. So the magma, basically in the mid-ocean ridges or in arcs, is what provides the heat, so the energy to drive the water, the hydrothermal circulation. But the metals does not come from the magma, mostly. That comes mostly from leaching of metals from the seafloor by fluids. So basically we have under the sea water percolates through fractures and cracks, and basically is then heated up by the magma source that causes it to ascend and vent on the seafloor. And examples of mid-ocean ridges, or past mid-ocean ridges where this process occurred and where mining has been active is the portals of Ophiolite in Cyprus. Not all submarine volcanoes are however on mid-ocean ridges, and this is an example of the Havre caldera, which is located up north of New Zealand. It's a submarine volcano, which was actually active quite recently, I think a couple of years ago. Doing lots of small eruptions, but nonetheless. And deposits associated with, well, this type of volcanoes, which are kind of more felsic compared to mid-ocean ridges, hosts of copper, lead, and zinc as well. And in order to preserve deposits, and basically these are some images taken underwater of these venting sites. As I was saying, in order to preserve the deposits, we have to kind of bury them quite rapidly to prevent them from oxidize. So how these VHMS deposits form is not just precipitation or settling of sulfides from these hot fluids. It is more complicated. We also have growth and replacement after while the mound is growing. So whereas in an early stage we've got this generation of let's say sphalerite and galena, either as massive sulfide or as stockwork. Later on, as the mound is growing and the temperature evolves through the mound, the sphalerite and galena kind of move outwards, and the core of the system will then be dominated by chalcopyrite. And again, later on, as the system evolves even more, the hotter part of the system will be mostly massive pyrite. So we've got this transition from massive pyrite, chalcopyrite, sphalerite and galena as massive ores, as well as disseminated ores on the outskirts, on the system, or as stockworks, where we've got veins and veinlets in the core of the system. And then, as I said, in order to preserve this, we need something that comes along, larger than volcanic eruption maybe, and there is everything to preserve it. So some prerequisites for this type of deposits are a heat source. Well, we need magma at some depth to drive the hydrothermal circulation. We need the water depth to be larger than 1 kilometer. Otherwise, boiling and metal separation would occur in the subsurface, and therefore you will end up with disseminated ores rather than massive ores. And we also, as I said, need rapid burial to prevent mineral oxidation. One example of a VHMS deposit is Golden Grove, where I spent a few weeks over summer. And this is hosted in day sites and undersites, and you can see this is a stratigraphic column of the regional geology. Basically, we've got a series of lavas and tuffs and breccias and submarine sedimentary rocks. And in certain horizons, we find disseminated to massive pyrites, sphalerite, chalcopyrite, pyrrhotite as well. And then at the end, there was this big eruption of undersite and daysite to bury the whole system. And this is just what it looks like today. It's actually an underground mine. But this is what the mineralized region basically looks like at the surface, where we've got this gossan. And we will look at that, what a gossan is next Monday. Because it really oxidizes its own off an ore deposit. And that's just a picture of a massive pyrite, chalcopyrite band. And well, I probably obviously thought that the ripple marks were more impressive than the massive ores, because I was smiling from them. Understand? This is not from that Golden Grove deposit. This is from an exploration drill hole in Canada, where again you can see a sequence of volcanic rocks intercalated with these massive brown sphalerite. And again, so this is actually a picture that was submitted together with a report to the stock market, and probably the share of this Cogito went through the roof on that day. VHMS deposits have also been mined in the 60s up in Northland near Bangarei, and these were mostly disseminated to slightly massive pyrite, chalcopyrite, that formed a mid-ocean ridge in the Cretaceous. And they are not mined for copper these days, but some people, they are prospective for gold. The next deposit along the spectrum is SEDEX, which stands for sedimentary exhalating. And these are usually deposits that are mined for lead and zinc, plus some silver. And were formed basically, let's say, immediately below the seafloor at the same time, or nearly the same time, just before, just after the rock they are hosted within. They form in advanced stages of continental rift, so within sedimentary rock units. where volcanic rocks are not preponderant. So whereas VHMS deposits, we had basically a system developing proximally to volcanic system. In SEDEX deposits, we might have some volcanism going on, but at a distal region, and the deposit forms basically without direct influence of volcanic fluids. And therefore, these are formed at relatively lower temperatures. And an example, interesting example of SEDEX, which is basically forming these days, is from the Salton Sea. So this is the western US and Baja California. California up here in Mexico. This is the Colorado River flowing down towards the sea. And in early 1900s, people built a canal for irrigation, and the canal basically broke its levees, and all the water from the Colorado River flowed out and formed this inland sea. It was just 2 years until they managed to fix the canal and stop the water flow. But what happened afterwards? Well, this region is within a rift. Okay. Well, we've got the San Andreas Fault up north, and then the rift between Mexico and Baja California. So it's a region of higher heat flux in the crust. So water from the Salton Sea started to percolate through fractures and cracks in the crust, and started being heated up. So we basically started forming this scavenging of metals by solutions and pre-precipitation at lower temperatures. And this is what SEDEX deposits often look like, very finely banded